The complex number z has a real part and an imaginary part. The real part is x, the imaginary part is y. Not iy, but y. X and y can in general be elements of the real numbers, and by pairing real numbers in this fashion we generate a complex number. Now the complex number can be represented graphically in the following manner. We have coordinate axis, the horizontal axis we call the real axis, the vertical axis we call the imaginary axis. Now a point in the plane, this is called the imaginary or the complex plane, and we can pick a point z equals x plus iy in the complex plane. We go out an x value on the real axis and up a y value in the imaginary axis. And this is our point z in the complex plane. This is called the rectangular form. The rectangular form of representing a complex number. We also have what's called the polar form, or the exponential form, and we represent that using a magnitude and an angle. The magnitude, we'll call m, is just the distance from the origin out to the point, and the angle is what we sweep that vector through from the real axis to align ourselves with the point. So the polar form has this representation, a magnitude m times e to the I theta. And we can also represent this in what's called the trigonometric form. And the way we do that is we represent x in terms of trig functions. This value here is a projection of the magnitude down onto the real axis. So this has value cosine theta times the magnitude m. Looking at a right triangle here, this projection is m cosine theta, and this projection is m sine theta. So the trigonometric form is m cosine theta plus I m sine theta, and we can see that m cosine theta is the x, the m sine theta is the y. And the m is going to be the square root of the sum of the squares. If we, let's look at m squared. This would be m cosine theta squared plus m sine theta squared, which is m squared times cosine theta squared plus sine squared theta. And this is a trigonometric identity equal to 1. So that's just equal to m squared. This is our x. So that's x squared. This is y squared. So m squared equals x squared plus y squared. M is called the magnitude of the complex number, or its modulus. Now, there's an infinite number of ways in which we can represent the complex number z. If we look at the polar form, z equals m e to the I theta, and what that means is we take a magnitude m, a vector of magnitude m, and we sweep it through theta. Well, we can get to the same point if we rotate once around. So if we add 2 pi n, any integer multiples of 2 pi, we get to the same spot. So for example, this is z is m e to the I theta. If I add 2 pi to the angle, I get back to the same place. And then if I keep going around again and I add 4 pi, I'm also back to the same spot. So if we add any integral multiples of 2 pi, we get to the same point in the plane. So there's an infinite number of ways we can represent z by just adding 2 pi multiples to its angle when it's represented in polar form. Polar form or trigonometric form is the only way we can do this. We cannot represent more than one value, the principal value for z in rectangular coordinates, because as we come back we always have the same x value, we always have the same y value. There's no way of differentiating whether we've gone once, twice, or 100 times around by the rectangular representation, but in the polar representation we can. If we go for the principal value, is those values that lie between 0 and pi in this case. So if I have, say, z equals 1 plus I, this is square root of 2 e to the I pi over 4. Now, this is also equal to square root of 2 e to the I pi over 4 plus 2 pi. And so on. We can add integral multiples of 2 pi to represent z. So the representation in polar form, if we allow multi-values, it is not unique. This particular one, we're between 0 and 2 pi. This is called the principal value. Now, if we raise z to an integer power, say we have z raised to the k, where k is an element of the integers, we can represent this as z to the k. What we do is we put z in polar form. So we have m e to the I theta plus 2 pi n, where n is an integer, and we raise that to the k power. This is our z. We're raising z to the k power there. Now, we can show this graphically. In the following manner. We'll get back to the complex plane. We have the real and the imaginary axis. Now, if we say this represents our complex number z, where we have a magnitude n and an angle theta, and we raise this to the power k, what's happening is, using the property of exponents, we can distribute the k through. This becomes m to the k times e to the j k theta plus 2 pi n. Or I can write this as m to the k e to the j k theta plus 2 pi n k. Now, what we can interpret by looking at that is that if we have a complex number z and we're raising it to an integral power k, m gets magnified by k. We raise it to the k power, and the angle that we start with has a factor k. It's multiplied by k. So in the complex plane now, our z to the k has a magnitude m to the k, and the angle is theta times k. It's k times larger than what we started with. So in effect, raising a complex number to an integral power rotates the vector that represents the position vector that represents that complex number. It expands the vector out, makes it longer, and it rotates it. So what we can do is say, all right, this complex number, then this is the base or the principal value, and then as we take on different values of n to get the other values, we're just rotating the vector even further along in order to get the other values that represent the complex number as we increase or decrease n by an integer. What happens is we always come back to the same spot, because what we're adding are multiples of 2 pi as we increment n. N is going to be an integer. We've increased it initially by 2 pi times k, which is just a multiple of 2 pi, and then by incrementing or decrementing n, we're just moving it along, rotating it another 2 pi or a complete revolution. So we always end up back to the same spot. The bottom line here is when k is an integral power, we raise a complex number to an integral power, k, where k is an integer, we always end up back at the same spot. It's a unique value. Now, even though it's unique, we may have an infinite number of ways to represent it, because all we have to do is tag along multiples of 2 pi to the angle. So we can just keep adding multiples of 2 pi, and we get back to the same spot when we have integral powers. Now, we could also evaluate a complex number to a power by representing the base in rectangular form. So if we take z to the k, where k is an integer, we could represent it that way. But in order to expand this out, we have to use a binomial theorem to expand this out, and it gets really complicated and messy if k ends up being a large power. This is not the way to go about evaluating a complex number raised to an integer power necessarily. It's much more efficient and easier if you use the polar form. But if you use the rectangular form as a base, you need to use a binomial theorem. For example, suppose we wanted to find out what 1 plus I to the 5th power is. Well, this is very easy in using the polar form for the base. 1 plus I is just the square root of 2e to the I pi over 4. Well, if we raise this, say, to the 5th power, this becomes square root of 2 to the 5th e to the I 5 pi over 4. So we get the answer rather readily using the exponential form for the complex number in the base to express the base. But now if we want to use the base in rectangular form, we have to expand this out using the binomial theorem, Well, to do this, first what we need to do is determine the coefficients that go in to each term, and we do that using combinations, or which is also revealed to us through what's called Pascal's triangle. If we set up Pascal's triangle in the following fashion, what we do is we start 1, 1, 1, and then we add the numbers up above to get the next row. So we have 1, 1 plus 1 is 1 plus 4 is 5, 4 plus 6 is 10, 6, 4 is 10, 4, 1 is 5, and 1. So this is the fifth row. This is for the expansion, I plus 1 to the fifth. So the way we write this is we take the first coefficient, which is 1, times then the first term raised to the fifth power times I, the second one to the 0 power, plus next term 5 is the coefficient. It's 1 to the fourth power I to the first power, plus then we have 10. This will be times 1 to the third power times I squared, plus 10 times 1 squared I to the third. We're decrementing on 1 and incrementing on I as we go along, plus 5, 1 to the first power times I to the fourth, plus 1 times 1 to the 0 times I to the fifth. Well, 1 times 1 to the fifth, this is just 1, and we have I to the 0, which is 1. So this term is 1, plus 5 times 1 to the fourth is 1, I to the first is I, so that's 5I, plus 10, 1 to the third is 1, I squared is a minus 1, so we have a minus 10, plus 10, we have 1 squared, which is 1, I cubed is minus I. Remember, I squared is minus 1, so I to the third would be minus I. And then we have 5 times 1 to the first is 1. I to the fourth is just 1. So this is 5. And then we have 1 times 1 to the 0, which is 1. And I to the fifth, which is I. So combining, we have 1 minus 10 plus 5, so we have 6 minus 10, or minus 4, and we have plus 5I plus I, which is 6I, minus 10I, which is minus 4I, so we can write this as minus 4, 1 plus I, which is I to the fifth. And we could get it into a polar form here if we want to compare. Is what we do is we take our minus 4, express this in polar form. 1 plus I is the square root of 2 e to the I pi over 4. And to bring the minus sign up, we have, let's say, 4 square root of 2, this part. Well, minus 1 is e to the I pi, and then we have e to the I pi over 4. We can combine those two. We end up with 4 square root of 2, and then e to the I 5 pi over 4. Square root of 2 to the fifth is 4 times the square root of 2. So we see that they are the same. But going the route of expressing the base in terms of the polar form is a much more efficient way to generate powers of a complex number. When manipulating powers of complex numbers, we need to make use many times of properties of exponents. So let's just review that first. If we let b be an element of the complex numbers, this is going to be the base, and r, s, and t are going to be elements of the real numbers, then b raised to the r plus s is going to be b to the r times b to the s. B to the 0 power is 1. B to the r power raised to the s power is we just combine the powers, multiply them together, and we could rearrange them and represent as this is b to the s to the r. We can swap the two powers. And also we have is if we have two complex numbers, b1, say raised to the r power, and another complex number that's different than b1, raised to the same power, we can combine the bases in the following manner. So those are the properties of exponents that we'll use. Now, we can show, say, some examples. If we take b to the r plus s and raise that to the t power, we can show that this is not equal to b to the r plus s raised to the t power. This is not the same. We taking b raised to the r plus s power, that whole thing raised to the t power is not the same thing as taking b to the r plus s to the t power. And let's show that. If we have b to the r plus s raised to the t power using this property right here, is we multiply through by t, so this becomes b to the r times b to the s raised to the t power. Using this property here, b raised to the r plus s is just b to the r, b to the s, and now we use this property to distribute the t through. We're using both this property and this property. Then this becomes combining b to the rt plus st using this property. And then I'm going to factor out a t, so this becomes t to the r plus s. So we can see that the expansion of this is t to the exponent becomes t to the r plus s, not r plus s raised to the t power. Now, how about if we have something like the conjugate of z? Remember that if z is x plus iy, z conjugate is defined as x minus iy, and in exponential form, z is e to the I theta, and z conjugate will be m, the magnitude, e to the minus I theta. What we do is we take minus the angle. That's what the conjugate is. If z is at angle theta, its conjugate is at minus theta. So z conjugate raised to the r power is equal to z to the r conjugated. We can flip the conjugation and the exponentiation. This is true, and let's show this. Well, z is equal to magnitude e to the I theta. Then z conjugate is its magnitude e to the minus I theta. So we can write now z to the r conjugate, putting in the exponential form. What we have here then is m to the I theta, oops, this will be z to the r conjugate Well, z is m e to the I theta. That's going to be raised to the power r and then conjugated. Well, distributing through with r, we've got e, or m to the r, e to the j, r theta, and that's conjugated. So this becomes m r e to the minus I r theta. This is the conjugate. Now, what we can do here is factor out the r, pull the r out. We can write this as m e to the minus I theta to the r power. Because remember, we distribute through with the exponentiation. Well, this is the conjugate of z. So this is z conjugate raised to the I power. We started with z to the r conjugated, and we end up with z conjugate taken to the power r. Now what happens if the exponent on z is fractional? No longer an integer, but will now allow fractional exponents. If it's fractional, we'll get multiple values for z raised to the a power, where a is an element of the rational numbers. For example, let's let a equal 1/5. And so z to the 1/5 will be m e to the I theta plus 2 pi n to the 1/5 power. Now, taking the exponent on through, this becomes m to the 1/5 e to the I theta plus 2 pi n divided by 5. Or we can write this as m to the 1/5 e to the I theta over 5 plus 2 pi over 5 times n. Now, as we increment n goes 0, 1, 2, 3, so on, we see that as we increment n, we're adding 2 pi over 5 to the angle. And we have to do this 5 times before we get back to where we were. So to represent this in the complex plane is, let's say this is our z. This is the magnitude, this is the angle. Now, if we take z to the 1/5 power, we're reducing the magnitude by taking the 5th root of m, and we're also reducing the principal value of the angle. We started with theta, now we're going to be at theta over 5. So our 5th root will be down here somewhere, where this is m to the 1/5, and this is theta over 5. So this is z to the 1/5. Now, when we increment on n, we're adding 2 pi over 5, or 72 degrees on each step. So this is when n equals 0. Well, when n equals 1, we're adding 72 degrees, or 2 pi over 5. So now the next value is there. To this value, we increment again with the same amount, 2 pi over 5 added to the angle. And then we add to the angle the same step there, and then again the same step. and then the same step, and we're back to where we started after 5 increments. Now, it turns out that, as you can see here, as we increment on n, all the values lie on a circle whose magnitude, or the radius of that circle, is the 5th root of m, its magnitude. So all the values of a complex number raised to a fractional power will lie on a circle with radius of the nth root of m, depending upon, or the kth root, depending upon what root we're taking, and then we increment the steps by the original angle divided by the power on the root that we're taking the complex number at. So we just keep incrementing around the circle. So in general, z raised to the 1 over k, where k is an element of the integers, it has k unique values. It's multi-valued. It has k values. And these are called the roots of z. And it will be cyclic. The steps will end up being 2 pi over k. That's the angular steps between the roots as we go around. They'll be evenly spaced on the circle with that angular step between each of the roots. Now, we need to be careful, though, when we're dealing with rational powers of complex numbers. For example, the identity b to the z raised to the u power, where both z and u are complex. Normally, with real numbers, we know that to be true. We can multiply the powers. But this is not generally valid for complex powers. The identity is valid for arbitrary complex z when u is an integer. This is always true when u is an integer and z is complex, and b is complex. But some identities for powers and logarithms will fail for complex numbers, no matter how the complex powers and logarithms are defined as single-valued functions. If you try to define exponentiation, logarithms, and so forth as single-valued functions, you're going to run into trouble with complex numbers. But if you consider exponentiation as a multi-valued function, all the identities hold. Same with the identities of, say, complex number u times the complex number v raised to the complex x. We can write this as u to the x, v to the x, or say u over v raised to the x power. This would be u to the x over v to the x, provided that v is not 0. This will hold true for all complex numbers, provided that the complex numbers are not 0, identically equal to 0. So these identities hold as long as you allow the complex numbers to be multi-valued. You're not restricting yourself just to principal values. Now, unique values will be obtained if the u and v are positive real number and x is a real number. These are always unique. They're not multi-valued. And in the case where u and v are complex numbers and not 0, and x is an integer, this also holds. And the identities always hold again when we allow multi-valued functions for exponentiation. So, show how that works out here. As long as you're allowing the complex numbers to be multi-valued, you're not going to run into trouble. It's just when you try to deal with principal values that you can run into inconsistencies. Now, suppose I'm doing my calculations using principal branches for the functions and define the exponentiation to be single valued. I could represent 1, the number 1 is being 1 to the 1/2. We know that to be true. And suppose I choose to write it as -1 times -1 to the 1/2. -1 times -1 is positive 1 to the 1/2 gives us 1. But this is not equal to -1 to the 1/2 times -1 to the 1/2. Well, if I distribute the exponentiation through, we know this to be I and this to be I. So we end up with I times I, or I squared, which is -1. So 1 is not equal to -1 when we're dealing with a single valued function. But if we consider 1 to be multi-valued, or the exponentiation to be multi-valued, we could write 1 as e to the I 2 pi. And 1 to the 1/2 is equal to 1. And this is as a single valued function, but we could write this as e to the I 2 pi to the 1/2. E to the 2 pi is 1. We're taking 1 to the 1/2, and this becomes e to the I 2 pi times 1/2. It's e to the I pi, and we know e to the I pi is -1. If we look on the complex plane, we go from 1, rotate it pi, we get to -1. So this is all, these are single valued. However, if you let 1 equal e to the I 2 pi n, where n can be an integer, so we have multiple values, that is, we can spin around. We start e to the I 2 pi, we can go around an integral multiples of 2 pi, we can spin around as many times as we want, we'll get to +1 as long as we just keep adding multiples of 2 pi to the angle. Well, in this case, 1 to the 1/2 becomes e to the I 2 pi n to the 1/2, or e to the I pi over n, and this is multi-valued, plus or minus 1. When n is even, it's +1. When n is odd, it's -1.